Professor Dimitris Giannakis from the Koopman Institute of Mathematical Science from New York. He has been there, he told me, for almost 12 years because he also served as a postdoc some time ago. He did his PhD in mathematics at the University of Chicago, and all his previous degrees were at the University of Cambridge. And today he will be talking on data-driven approaches for spectral analysis of ergodic dynamical systems. I think, if I remember, this will be our third or fourth presentation this semester on dynamical systems, so the pressure is up, as they say.
Okay. Thank you very much for coming and the hospitality. It's been a great day with a lot of exciting conversations. My goal for this talk is to give an overview of data-driven approaches for pattern extraction and prediction in dynamical system, combining some ideas from machine learning with operator theoretic ergodic theory, namely Koopman operators, which I understand have been discussed extensively here in the past few weeks. I would like to start by thanking my collaborators in this work, Tyrus Berry from George Mason University, Sudho Das, who's a postdoc working with me at Courant, John Harlim from Penn State, and Joanna Slawinska from Wisconsin, Milwaukee. Okay, so a picture is worth 1,000 words, they say, so let me just start by showing a picture of the state space of a dynamical system. So the well-known Lorentz 63 equations, which are defined in R3, so three-dimensional space. And what is shown in this picture is a numerically generated evolution of these dynamical systems, which has the well-known property that the solutions collapse and concentrate near the famous butterfly attractor, which has this fractal, complicated shape. And color-coded here is a function of the state of the dynamical system, which basically just shows the first coordinate of the state vector. So blue here corresponds to large negative values, yellow and orange corresponds to large positive values. So this is an example of an observable of a dynamical system, namely a function of the state. And now, as the system evolved, or associated with every such dynamical system, is a corresponding action on the space of observables. Namely, what we can do, we can take an observable, our observable rather, and plot it and use the same basically color-coded scheme, but now the colors, we're going to take the colors from the original picture and map them and assign them to the point that the system reaches for evolution, after evolution over a given time interval. So phi here is the flow map, is essentially the solution of the ODEs that describe the Lorentz 63 system, and this shows correspondingly the evolution of the observable f after time t equals 0.2. So you can see that basically the original color scheme is now kind of moved forward under the dynamical evolution, and it is a well-known property of chaotic dynamics of the Lorentz 63 system that as time goes on, this observable is going to become increasingly mixed, so to speak. This is evidenced by the fact that you can see blue colors in close proximity with yellow colors in this color coding scheme. And so at a time which is, you can get an order of magnitude estimate based on things like Lyapunov exponents. So here at a characteristic time of approximately 1 natural time unit, you can see that this observable, namely the position of the x1 coordinate of the state vector, sort of start to look like equidistributed, strongly mixed on the Lorentz attractor. So this is a manifestation of chaotic dynamics. Now, what I want to do next, I want to compare the evolution of this observable, the x1 coordinate that I was showing before, with this other one, which is an observable that has this form at time t equals 0, and this is an observable that is sort of data-driven. It is determined through the techniques that I'm going to talk about later. And I want to compare their evolution with respect to time. And I guess the one message that I want to get across is that you can have a fixed dynamical system, so the same dynamical systems, but different observables will exhibit different coherence in time. under the dynamical evolution. So here you see that the x1 observable is already mixed, starts to get significant mixing after, in this case, 0.4 time units. This other observable maintains sort of, at least by the I norm, maintains a coherent structure on the attractor. And in fact, we can continue more. After one time unit that we were showing before, this still maintains the same qualitatively similar features. And now if we start going at later times, so now we're doubling the time, the step size of these times, this still maintains a reasonable amount of coherence. Now, of course, this is a mixing dynamical system. Every observable eventually will become mixed. And this is no exception, but it holds its coherence properties over significantly longer periods of time than, let's say, the x1 observable. So I guess one message here is that for a given dynamical system, there might be different observables that exhibit different coherence properties. So therefore being more or less predictable, if you wish. Right? And so the goal of the techniques that I would like to talk about today is basically twofold. On the one hand, we would like to identify coherent observables of the system, like the one that I showed previously. And we would also like to predict these and other observables. And we would like to do that given in a data-driven manner, that is, given a time series of measurements of some observable, which may or may not be the one that we would actually like to predict. Ordered in time. So we assume that we have a time-ordered data set and no information about the underlying dynamics. And we would like to achieve these two, broadly speaking, these two tasks. Okay, so this is a summary of the work that we've been doing in this area, and I would like to discuss today. On the one hand, I want to talk about the general problem of approximating these underlying evolution operators. These are the Koopman operators from data, for example, in this chaotic Lorentz 63 system, and then talk about the problem of identifying coherent observables through computation of Koopman eigenfunctions. And finally, this is our kind of like more recent work on this area, is to develop this notion of coherence through eigenfunctions in the case that in systems that exhibit a so-called continuous spectrum. I will describe what that means later on, but essentially these are systems with chaotic dynamics for which Koopman eigenfunctions may not exist, and you want to find some kind of replacement for that. And the main tool we will use there will be the theory of reproducing kernel Hilbert spaces, which is used extensively in machine learning in order to do that. So feel free to ask any questions during the talk. I may or may not have enough time to go through this last part in detail. Okay. So I just want to, this is maybe a little bit of a daunting slide, so don't pay too much attention to it. I just want to set up the assumptions. I can just do it in, let's say, plain English without, worrying too much about the notation. So what we're assuming here is that we have some dynamical flow on a manifold. So the case that I would like you to think about is that the manifold here would be the R3, for example, in the case of Lorentz 63, just to have this always in mind as our prototype example. And we're going to assume that this dynamical system exhibits some ergodic behavior. So that means that the flow has an associated invariant probability measure, which is also going to be ergodic. So this means two things in the context of this assumption: that there is a set where all the probability mass is effectively concentrated in sufficiently long times, and this will be, you can think of this as the Lorentz attractor in this case. So A you can think of as attractor. And we imagine that there is, the Lorentz 63 possesses these properties rigorously, but we're considering systems in the class of having these properties, and we observe the system through a observation function. Previously, it could be, for example, we observe the full state vector in the pictures I shown, or it could be a subset of the components of the state vector. And we have a collection of measurements of the system obtained at a finite time interval. There are some additional technical assumptions here. Don't worry about this too much. So again, as a basic setup, you can think of the Lorentz 63 as our prototype system that we would like to model. Okay. So I guess there have been a number of talks on this topic here recently, but we're going to approach this problem from the perspective of the operator theoretic description of ergodic theory. So this perspective basically places the focus in the study of a dynamical system, not necessarily on the action of the flow map in state space, which can be highly nonlinear, as in the case of Lorentz 63, but instead it characterizes a dynamical system through its action on observables. So observables are basically functions of the state, and the distinguishing aspect of this description is that spaces of function spaces on a potentially nonlinear set are intrinsically linear spaces. I mean, this is because, for example, we can add two functions together and we can get back a new function. So there is an addition operation. We can scalar multiply a function, we get another function. So the space of functions on some potentially nonlinear set, or let's say the space of complex valued functions, is a linear vector space. And so examples here, what we would consider in our study could be, let's say, the space of continuous functions on the Lorentz attractor, on A. So this space is a Banach space equipped with a supremum norm or the maximum norm for continuous functions. So it has additional structure than merely being a linear space. Or we could consider a Hilbert space, the L2 space associated with the invariant measure of the system, which now has also an inner product with it. So once we fix an appropriate space of observables, then we can define, or under some conditions on the space that we fix, a Koopman operator, which basically is a linear map that maps the space that we chose back to itself, that acts by composition with a dynamical flow. So what do I mean by that? I mean that if you supply an observable f, like the one I showed earlier on from the x1 component of the state vector, there is an operator ut, the Koopman operator, where t here is a time parameter, that acts on f by producing a new observable. And if you want to evaluate that new observable at a point x, what you have to do, you have to evolve first under the dynamical flow map over the time t, and then evaluate the old observable, the one you supplied, at the point that you reached. So it is a composition operator in the sense that it composes observable with the dynamical flow. And so we're going to characterize the dynamics through ut instead of phi t. Now, the advantage of this approach is that this operator here, as defined, is actually an intrinsically linear operator without making any approximation like linearizing the dynamics. The potential disadvantage, or at least let's say one challenge, it's that spaces like the continuous functions on A, L2 spaces, and many other spaces of observables are going to be infinite dimensional spaces. So you can think of what is happening here is that we're going to represent a nonlinear dynamical system on a finite dimensional space through linear operators acting on infinite dimensional spaces. So we're trading off effectively nonlinearity with infinite dimensionality. So now this might appear to some extent an unnecessary increase of complexity by going to an infinite dimensional space, but at the same time it gives us a lot of structures. Namely, there is the fact that these are Banach or Hilbert spaces allows us to perform basically to deploy all the machinery we have available from techniques like functional analysis to approximate these operators in a consistent manner. So we have tools available to us that focus precisely on approximating linear operators on infinite dimensional function spaces. So our approach, I mean, this has been recognized for a number of years now in the literature, in the design of data-driven analysis techniques for dynamical systems. Our approach of the techniques that I will present here is that we make fairly extensive use of kernel methods from machine learning in order to allow us to build these approximations from data in a data-driven manner. That's the main goal here. Now, before I describe how exactly this happens, I want to just say a few words about some additional properties that will be useful for us to keep in mind, particularly when it comes to understanding a notion of coherence of chaotic dynamical systems. So what it turns out, so if we focus on the action of the Koopman operators and these L2 spaces, so it turns out that these are unitary operators. So that means that their adjoint is equal to their inverse. So you know, for example, what is a unitary matrix in Rn. It is a matrix that, or an orthogonal matrix that basically performs rotations. So in this case, in this L2 setting, the Koopman operator is you can think of as an infinite dimensional analog of that picture. And what is also a property of linear algebra is that you can take, for example, if you start from a skew symmetric matrix, if you take it exponential, you're going to produce an orthogonal matrix. So there is behind, let's say, an orthogonal matrix that performs a rotation, there is a so-called generator. This is like, in this case, a skew symmetric matrix that describes basically an infinitesimal, quote unquote, rate of change of rotation. So it turns out you can do the same thing in the setting of Koopman operators for measure preserving dynamical systems. In particular, there is a so-called generator of the Koopman group. So this group of operators can be completely characterized through its generator. Now the generator acts on observables kind of like, as I said before, for the generator of rotations by computing this limit. So it's kind of like a time derivative, if you wish, along the action of the Koopman operator or along the dynamical flow on observables. And this operator has the property that is a skew adjoint operator. You can think of that as a generalization of an antisymmetric matrix in this infinite dimensional function space setting. So this operator is quite fundamental in the study of the unitary Koopman group, because it turns out that you can describe it by in terms of this spectral, so-called spectral integral. So what this is doing, I mean, maybe this notation is a bit unfamiliar, but let me try to give you the gist of it. Basically, it introduces a quantity called a projection valued measure. So this is a quantity that you can integrate against, kind of like you can integrate with respect to the Lebesgue measure, but the output of integrating against a projection valued measure is not a number, but it is actually a projection operator, as the word says. So you can think of it as a map where you specify, let's say, a subset of the real line. You can think of it as being a frequency band. It's like let's say I choose some time scales of interest that I would like to focus on, and I can represent this as a frequency band. And for every such choice, the projection valued measure outputs a projection operator that essentially takes observables of the system and projects them down, or selects the frequency components corresponding to the frequency band that I chose. That's one way of thinking about it, perhaps closer to, let's say, filtering or spectral analysis of time series. And you can perform a meaningful notion of integration. So namely, if I have this projection valued measure, if integrated times this quantity here, so over all frequencies, and this I here is the complex number I, if I integrate I omega against this projection valued measure, I get back the generator. Now, and similarly, I can define functions of the generator, so exponentiation, by integrating the function that I want to produce, like this is a scalar valued, complex valued function, against the projection valued measure. And that gives you back the Koopman operator. So there is this ability to go from the generator to the Koopman operator through this integral. This is known as a functional calculus. It allows us to compute functions of operators. And this is some structure we would like to exploit later on. Just to give it, maybe to make it a little bit more connected to what, for example, one might encounter in Fourier analysis of time series. So there is this spectral measure, the projection valued measure, and for every observable in L2, you can define, using it, a real valued measure, which in some sense you can think of it as being a Fourier transform of the autocorrelation function. So it's like some kind of power spectral density. So if I take an observable, I can compute its time autocorrelation functions through this inner product. So that's the Koopman operator acting on the same observable inner product with itself. And it turns out that that power spectral density enters here in this computation of the autocorrelation function. So basically, for every observable, you could do a sort of like a time series analysis or like a spectral analysis of its autocorrelation function, and underlying this whole structure will be the projection valued measure of the dynamical system. So this is like something which presides over all these autocorrelation functions and their spectral densities that you might generate by observing the dynamical system. Okay, so these are things that we want to keep in mind. Okay, so let me talk about how one might approach the problem of performing prediction using this language. Now, in the prediction problem that I would like to focus on, there will be a statistical prediction, which means that what we're interested in doing is computing expectation values of observables with respect to some probability measure that characterizes our knowledge about the state of the system when we initialize the forecast. So in the language of Koopman that I just described, essentially what we want to do, we want to compute the expectation value of, in order to make a prediction, at time t, we want to compute an expectation value with respect to that probability measure of the observable of interest acted upon by the Koopman operator. And that expectation value you can actually express as an inner product in the L2 space with respect to a density, with respect to a probability density, assuming that the observable, assuming that the initial probability measure has an L2 density to begin with. And so now once you can phrase this problem as an inner product, now you can talk about how am I going to approximate this inner product in using basically matrix algebra, so finite dimensional approximations. So for that, what is enough is that if you're given some basis for your space, you can project down all observables into the basis, and in particular onto spaces, finite dimensional subspaces spanned by the basis element, ordered in a particular way, and instead of computing this inner product, which involves various integrals of these Koopman operators, you can approximate it by projecting down your observable and your probability density onto this basis. And when you write down the formulas numerically, this ends up being just essentially computable in terms of matrix vector products, essentially in terms of matrix algebra. What goes on in this computation is that you say, okay, I have a basis, think of it, let's say, like a Fourier basis on some domain. If I'm given my initial probability density, I compute the Fourier coefficients of the density in the basis. I do the same for the observables. I have, again, a bunch of Fourier coefficients, which I can represent as a vector. And then I can represent the Koopman operator in that basis, because remember, this is a linear operator, through its matrix elements. So if I have knowledge of these quantities, so this is a matrix whose elements are labeled by the basis element acted upon by the Koopman operator, I can compute this quantity as a matrix vector product, in a sense. And that, as the number of basis functions goes to infinity, this is going to converge to the true expectation value. So this is a basic observation from linear, essentially from the fact that this is a bounded linear operator. Now the question is, in real applications, we're not going to be handed a basis, right? We have these operators, there is this underlying structure, but we don't know, for example, what is the invariant measure of the system. We do not know what is the geometry of its support. It could be something like the Lorentz attractor, which is a highly complicated set. So it is difficult, even though this is an attractive formulation, it is difficult to approximate this a priori. So this is where the use of kernel algorithms comes in our approach. We're going to use kernel methods from machine learning to approximate in a suitable way a basis of the L2 space, right? So once we have a basis with approximation guarantees, because this is going to be only an approximate basis, given that we're going to use a finite number of samples to construct it, then we're going to formulate these matrix representations, and so long as the basis obeys some convergence properties, as the number of samples goes to infinity, then this approximation is going to converge in the limit where the number of basis functions go to infinity. So what is here our main tool, right? So kernel methods is useful for constructing basis of function spaces because associated with them are integral operators which are computable from data. So what is a kernel to begin with? So a kernel is a function, it's a bivariate function that takes pairs of points in state space and produces a real number. So for example, I will show a specific example later on. You could consider a covariance kernel that is used in methods like proper orthogonal decomposition, or Gaussian kernel that is used in various types of manifold learning applications. So with such a specification, there is an associated integral operator that takes an L2 function and outputs a continuous function, because this is a continuous kernel, by performing this integral. So this is essentially like a weighted sum, a weighted average of f, of an observable f, weighted by the kernel. And so it's an integral operator, and its output is a continuous function. So this is useful because it will allow us to compute an orthonormal basis of this L2 space using eigenfunctions of this, or a related operator to that. Again, I don't want to go into this in the full detail, but what I would like to just to say for now is that you can take this operator k, which is an integral again over the state space, and you can compute an orthonormal basis of L2 consisting of associated eigenfunctions from it. And this is a problem that can be tractably approximated from data using, this is basically a widely used approach in machine learning, where this operator G here that I wrote down would be replaced by a kernel, matrix. And the idea is that given this operator, you have a dictionary, a set of basis functions that you can use to approximate then the Koopman operator. Maybe let me just show some concrete examples. So kernels here, for our purposes, they have to be data-driven. So what do I mean by data-driven? They have to be evaluatable solely based on quantities in the data space. So they have to have effectively a form of this type. So k of x comma x prime, it should be given, it should just depend on x through f. F, remember, is our observation map. This is the actual data that we observe. So when we have data in a data space like RD, we could define things like the covariance kernel or the Gaussian kernel, as I mentioned earlier. These are all examples that one might employ. There might be some technical reasons, for example, why Gaussian kernels are preferable to covariance kernels, let's say, having to do with essentially the richness of the eigenfunctions you can get from G. That has to do with the rank of these underlying operators. But these are just typical examples to show you how this works in practice. Let me skip some of the details. So basically, the idea is that in a practical setting, we're going to compute our basis using eigenfunctions of the kernel, and then essentially just syntactically just transcribe what I showed in the previous time in the continuous formulation from the quantities that we observe from in the base, from the finite data set. So in that setting, the Koopman operator becomes essentially like a shift map of time series. So if you have a time series which happens to be a sampling of some observable of the dynamical system, then the Koopman operator becomes like a shift map in forward shift in time of that time series. So we can use this whole structure to get an approximation for these expectation values. Let me show you a movie maybe to kind of like highlight how this works in pictures. So what I want to show here, oh, it started. Let me go in the beginning. So this is an experiment where we took the same Lorentz 63 system that I was showing previously, and we do the following thing. We have some training data which are generated from the system. This is again a time-ordered series of points where we have no a priori notion of the dynamics. But what this method essentially can do is to say that if you specify some initial probability density in the state space, so this is color-coded here as a probability, basically distribution on the data, on the training data set, then this method is going to basically learn an evolution for such densities under the dynamics. And what we want to do here, we want to compare that evolution that this method learned from doing a Monte Carlo simulation from using samples, initial conditions drawn from the same density and evolved in time using the true equations of motion. So basically this is like a consistency check where we want to see how close this data-driven model of the density approximates the true evolution. And so what this is supposed to show is that at least in the picture norm, you get a qualitatively consistent representation of the density. Of course, at later times, this mixes over all the attractor. But if you were to follow it, at least over initial times, there is a fairly good consistency between the data-driven approximation and the true dynamics. Now, we can look at this more quantitatively, if I'm able to go back to the presentation. Okay. Okay, so we can look at this more quantitatively by comparing the forecast skill from various methods. The two curves I would like you to focus on is this light green curve. This is showing the RMS error of basically predictions using the true model with this type of initial densities that I showed. And the blue curve is the RMS RMS error from this method that we call diffusion forecasts, because we use the diffusion maps algorithm to get the basis functions in this case. And you can see that it does a pretty decent job in approximating the true evolution, even though this method was given no a priori knowledge of the equations of motion. It also does a good job in approximating the forecast variance. So this is important for UQ. So you can do the same prediction experiment, but now instead of predicting the expectation of F, you can predict, for example, the standard deviation of F with respect to the initial probability density. This is shown in dotted lines where, again, this is roughly tracking the true evolution of the variance under the ensemble, and it has the correct asymptotic behavior at large time, whereas other methods that we tried were not, especially in the case of the variance forecast, were not doing such a great job. Okay, so this is to basically illustrate that with this linear operator perspective, we can get consistent representation of chaotic dynamical systems by virtue of the fact that kernel algorithms provide a basis for this Hilbert space of observables where we're interested in performing approximation of the Koopman operator. And this is done in a way that converges as the number of samples goes to infinity under realistic assumptions. However, what I haven't told you about is how is that related to the first problem that I wanted to talk about in the beginning of the talk, this notion of coherence. So in particular, the method that I just showed you takes no account of the spectral properties of the dynamical systems I was highlighting earlier. So now, when it comes to the problem of extracting coherence, the spectral properties of the system are actually important right from the outset. Namely, it would be hard to think of a kind of like an intrinsic characterization of coherence in this like measure preserving setting without reference at some level to the spectrum of the system. And in particular, what will be the focus here, and I guess that must have come up in previous talks on the topic, is the notion of Koopman eigenfunctions. Right? So a dynamical system will, in general, exhibit a class of distinguished observables, which are eigenfunctions of the generator, which have the property that under evolution of the dynamics, they evolve at a fixed frequency for all time. So this frequency, you can think of it as an eigenfrequency of the system. And so these are natural candidates for coherent observables, since essentially having an observable with one frequency is as coherent as you can possibly get. Now the thing is that a general dynamical system is not going to have only, rather, these eigenfunctions in general will not provide a basis for the whole Hilbert space. Namely, not every observable can be fully represented in terms of these Koopman eigenfunctions. And in fact, for systems that have chaotic behavior or mixing dynamics, there will be something called a continuous spectrum of the Koopman operator that will behave analogously in some level to, let's say, a noisy source. So it will generate a continuum of frequencies as opposed to a discrete set of, or a countable set of frequencies in the case of the eigenfunctions. And this continuous spectrum is not going to have associated eigenfunctions with it. So we have to think about how to define an appropriate notion of coherence in that framework when we deal with the continuous spectrum. Let me show you, before I move on to how do we address that, since I'm conscious of the time here, I want to show, and I can talk about the details more offline, if you'd like to, just an example of computing Koopman eigenfunctions from some dynamical system using our approach, which again I haven't been able to describe in any detail, but just to give you some basic idea. So what we take here is a dynamical system which is defined on a two-dimensional torus. So it's like a two-dimensional rotation, if you wish. So if there are two angles that characterize the system, and it has this type of vector field. So these are an example of an orbit of the dynamical system. This is chosen to have sort of a variable speed on the torus as a function of position, which, if you look at the corresponding time series obtained by basically taking this donut and putting it in R3, so this torus embedding in R3, it produces this rather, let's say, somewhat complicated looking time series, which are basically what the algorithm gets presented. So they have different time scales, they are aperiodic, and they have some sort of at least apparent complexity. But of course, this is a system where it has a pure point spectrum of Koopman eigenfunctions because it's defined through a set of separable ODEs. So these algorithms should be able to find that underlying structure of these Koopman eigenfunctions. And this is what I'm showing you, plots of the Koopman eigenfunctions, or the real and imaginary parts, plotted on the torus, again, as examples of observables like I was showing earlier for the Lorentz 63 system. So what these diagrams here are showing are the time series sampled along orbits of the dynamics of these observables. And what you can see that they are clearly basically periodic. They are evolving at a distinct frequency, at a single frequency, even though the time series that we put in as an input had basically a countable infinity of time series, if you wish, of frequencies. These are like the basic building blocks of the dynamical system, for this dynamical system that can be used to reconstruct any observable in L2, in this Koopman eigenfunction. So again, I didn't have time to describe exactly how this is done in detail. I also want to point out that I'm showing this toy examples here, but these are tools that we can actually apply for real-world data. This is an example of from an analysis of a climate data set. So these are observations, satellite observations of the tropical atmosphere, which are basically proxies for atmospheric convection, these big storms and so on that appear in the tropics. And we are finding here, or representing here through Koopman eigenfunctions, that they are shown here in these time series plots, different modes of kind of coherent convective variability in the tropics. This is just to highlight that these methods are applicable with real-world time series. Okay. But the thing is that what I've been talking about so far mainly addresses, at least from the point of view of this coherent pattern extraction, it mainly addresses the question of how to approximate Koopman eigenfunctions, which, as I said before, not every system will have a complete orthonormal basis of such eigenfunctions. For example, a chaotic system like the Lorentz 63 will have no non-trivial Koopman eigenfunction. It will just have a continuous spectrum. So the question then becomes what to do with this approach, how to generalize this approach in the case of systems with continuous spectrum. So for that, we're going to use a method of regularizing the generator, so regularization for this operator, mapping it, which will basically map it into an operator that has nice spectral properties. Namely, it will be an operator that has just eigenvalues and just eigenvalues. It will be a compact operator and an associated complete orthonormal basis of eigenfunctions. And this will be done in a manner that allows us to control the regularization in a manner that we can show convergence of the spectral properties of the regularized generator to the underlying Koopman operator. So I'm just going to give a nutshell of these techniques before closing. So the main idea here that we're using is this notion of a reproducing kernel Hilbert space. And as in the previous approaches that we used kernels, kernels here will play also a central role, but here we're going to assume that they have some additional properties that we didn't necessarily require earlier. And these are listed here. This is basically symmetry and non-negativity. So they have to have these two properties. And it's a well-known result that for every such kernel specified on the state space, there is a corresponding function, space of functions, called the reproducing kernel Hilbert space, that has two important properties. The first one is that if we take the kernel and we fix one input argument and leave the other argument arbitrary, that actually defines a function in the RKHS. But perhaps the most important property is that the so-called reproducing property, which says that for every function in this RKHS, we can evaluate it at any given point. So there is point-wise evaluation through an inner product. And inner products are basically bounded functionals on a function space. So we have the ability to perform point-wise evaluation by bounded and therefore continuous linear functionals. So this is an important property that you don't have, for example, in an L2 space This is widely used in machine learning applications and in kernel algorithms in order to do things like interpolation and out-of-sample extension of data. Here we're going to use it in the context of regularizing the generator of a Koopman group, which has potentially continuous spectrum. And the main property that we're going to employ is the following, namely that if we have a state space where we can, which has basically it has the structure of a differentiable manifold, like R3 in the case of the Lorentz 63 system, this is just an infinite, it's a smooth manifold. If we have a CR manifold, so R times differentiable manifold, we can specify a kernel that has the same differentiability class. And then what we automatically get is that the RKHS becomes a subspace of R times continuously differentiable functions on that manifold. Now, in effect, what this allows us is to encode the regularity that we want to obtain in H through the regularity of the kernel. And we can do that irrespectively of the fact that, let's say, the dynamics concentrates in a fractal attractor where there's no such notion as CR regularity, right? Here we can define a CR kernel despite the fact that the system has a Lorentz attractor, let's say, which doesn't have a CR structure, and we can still get an RKHS, which when viewed as a subspace of functions in the ambient manifold will have CR regularity. And that's a very useful property for us to have. I'll keep, how much time do I have? Maybe
10 minutes.
10 minutes, okay. I'll skip, obviously I'm skipping a lot of the detail here, but just to give you, a brief overview of how this works. So remember that we start, well, let me start from the following, right? So we have a kernel here, and we're going to require that is at least differentiable on the state space. Now, remember from the kernel, we can construct a associated integral operator. And now this operator will have the following property. Because of the C1 regularity of the kernel, all the eigenfunctions of this operator, or basically the range of the operator, will actually lie in the domain of the generator of the Koopman group. So it means that these are functions for which this unbounded operator, the generator, can meaningfully act, right? So now, if we take our generator, therefore, and compose it from the right with G, so this is like smoothing, because we're applying pre-smoothing, because we're applying G before V, we get a new operator, we call it here A, and this operator has the property that it is actually a bounded, compact, in fact, a Hilbert-Schmidt integral operator, which has, again, a representation in terms of a kernel. The kernel here is just basically the derivative of the original kernel. So basically, we're hiding all the nasty stuff that is happening here with the generator into the kernel, which we can differentiate because it's a C1 kernel, and we get this representation. So you can do this also in the opposite way, which is somewhat less trivial. You can do the smoothing from the left. You can also do the smoothing, let me skip here. You can do the smoothing from both sides by kind of like symmetrically. And this is what ends up producing an operator which is skew adjoint, because you multiply a skew adjoint operator from the left, from the right, by self-adjoint operators, and it's also compact. It has the same Hilbert-Schmidt property as before. And you can use this operator in a way as a compact approximation, if you wish, for the generator, which has the key property with skew adjoint. So this is like a structure preserving regularization, in the sense that one of the essential structures of the problem here is that it's measure preserving, so you have a skew adjoint generator. So we would like our regularization to preserve that structure, and we can, we can do it this way. And then we can look for eigenfunctions of this operator, this skew adjoint compactified operator, and this will form essentially analogs of the Koopman eigenfunctions, but now defined irrespective of or not of the presence of a continuous spectrum. I'm skipping out a lot of stuff. We have a notion of convergence of these methods, which again I don't have time to describe. that there is a regularization parameter that allows us to control the convergence of this skew-adjoint compact approximation to the generator to the original Koopman operator. Okay. I will skip, so I will just show some numerical examples to end the talk from this method. And first, this is more like a sanity check. I'm showing you a similar torus rotation as before, where there is a point spectrum to begin with, that the eigenfunctions that we get from this compactified generator are consistent with Koopman eigenfunctions, as they should, because if the system does have Koopman eigenfunctions, we would like to be able to approximate them, and this is true. But then we can also apply this to the Lorentz to a system like the Lorentz 63, which in fact here there are no Koopman eigenfunctions, so you're not going to be able to get observables that viewed as time series are purely periodic. But what this method does, it tries to do like the best next thing to, let's say, a periodic observable. It produces things that qualitatively resemble these like wave packets. So they have a fairly coherent frequency context. So they're fairly peaked in frequency, but of course they're not delta functions, so to speak, as it would be the case for Koopman eigenfunctions. And they tend to have these like amplitude modulating envelopes. So they look a little bit like wavelets in a way, but wavelets that are somehow, we haven't have any rigorous results to that, but they are they behave qualitatively like wavelets tailored for the underlying dynamical system. This is the example of the pattern that I showed in the beginning of the talk, where you can see that it has this low, slow, like coherent frequency evolution. They come at different time scales, and plotted as functions on the Lorentz attractor, they exhibit sometimes this kind of like localization property, where they just localize in different parts of the attractor, where things can be approximated in sort of like a quasi-periodic way, perhaps. Okay? So this approach can also be used for prediction, not just for coherent pattern extraction. I'm just showing here an example where we're predicting the Lorentz 63 model with this method. Obviously, the forecast is going to go, degrade over time because this is a chaotic system, but you can see that at least there is some consistency over intermediate times. I should say that this is a stronger result than what I was showing earlier, because this is not just statistical prediction at this point, meaning the initial data here are not a probability density. We have initial data that are specified point-wise, and this method produces a forecast time series as opposed to a forecast of the expectation value. Okay, and this is other example with the Rossler system. This is a fairly new work, so we haven't yet applied it to something like the climate. What we are in the process of doing that. So I will leave this as a summary slide. What I was trying to illustrate here is that combination of machine learning techniques with operator theoretic formulation of ergodic theory is a useful way of addressing the problem of coherent pattern extraction and prediction in different kinds of systems, in particular systems that exhibit either pure point spectrum, mixed spectrum, or coherent continuous spectrum. And we're, I think, here only just scratching the surface. There is a lot of interesting questions and potential applications of this work that we're hoping to address at some point in the future. So I'll leave it at here, and thank you very much.
Any questions? Yes,
Yeah.
go.
So allowing this, I'm just curious, with these data-driven approaches, so you mentioned that, so if you have enough data, you can formulate these basis functions, but basically what happens if you go, which that's common in, this age that we're in, but what happens when you go to the very data sparse section? Can do these extrapolate over to like that area?
Yeah. So the question was how these methods behave in the sparse data regime where sparsity here means you don't have a lot of samples in the attractor? And that's a very good question. So let me start just by saying that this method makes very few assumptions about the underlying system, in the sense that it doesn't require an explicit parametric form of the dynamics. It makes implicit assumptions about ergodicity and things like that. And precisely the fact that precisely because you don't make many assumptions, you have to make up for it somehow differently. And data is how you make up for it here, right? You need to have sampled the state space in an adequate manner. And obviously the number of samples you will need in order to do that will depend strongly on, let's say, the dimension of the underlying attractor, right? For systems like the Lorentz 63 system and all these like torus rotations and these toy examples, it's something that you could run on a laptop, with a fairly small number of like few thousand points. Now, of course, when you go to a real-world application, it's unrealistic to expect that you will be, with a real-world sized data set, you're going to be anywhere close to the amount of sampling that we're producing, for the toy systems. Yet these methods seem to, do a decent job in a whole range of problems, like examples from the climate or fluid dynamics, which I didn't talk about today, where these methods do have some success. And now the reason I believe that where these methods might be helpful are in situations where the system itself, despite being very high dimensional, if you wanted to model it in its every gory detail, exhibits nonetheless at least some low dimensional effective dynamics, or to put it differently, maybe in a language which is more appropriate to here, it exhibits some observables that can be well approximated from modest amounts of data. So this is a different problem to say I want to approximate every observable, like in the L2 space, as opposed to saying that I want to approximate maybe just a relatively modest subspace of the L2 space, and maybe in that space I can find interesting things to look for. Just to give an example from climate, so the climate has different sort of coherent modes of evolution. You hear about the El Niño phenomenon, which is somehow like an oscillatory behavior. It's not like a clockwork phenomenon that happens, at some kind of fixed frequency, but nevertheless it does exhibit some coherence in time. And so for phenomena like that, these methods, could be potentially competitive, I think. If you want to ask, can I model, the fine-scale effects of turbulence with this approach, I would not be so confident as to say yes. But just to wrap up and give an answer to your question, I think the ability of these methods to operate in sparse sampling depends very strongly on whether there are observables of the system that are interesting to you, or for prediction, that can be well approximated through like the leading few eigenfunctions of these integral operators. Such observables could be estimated using modest amounts of data.
So one question is, what happens if these transition matrices are too big even to compute those eigenfunctions? Is there any way to approximate even those transition functions? Those transition matrices? You mean for the kernel or for the Koopman? For the kernel.
Yeah. So for the, let me repeat the question for the audio. That the question was, what can be done to approximate in situations where the kernel or the transition matrices are too large to explicitly compute their eigenfunctions. So for that, there are a number of, this is more of a technique which is kind of related, as opposed to machine learning, meaning like there are a number of ways of addressing that which have been developed in the machine learning community. One way that is employed sometimes, if you are in situations where you cannot even, there's no way for you to solve this eigenvalue problem, you can subsample the data, and then there are methods that called like Nystrom extension that allow you then to fill in some kind of approximations to the things that you were not able to include. One thing I should say is that the kernels that we typically use in this work are Gaussian kernels which have exponential decay that allow us to approximate the kernel matrices by sparse matrices without us having to do subsampling first. So subsampling we would do, let's say, as a last resort if, despite the sparsity of the matrices that we employ, we can still not solve the eigenvalue problem. But all of these are questions that are, they're not specific to this. They're basically, broadly applicable for, kernel algorithms.
Well, let's thank our speaker.